When it comes to Tesla Optimus, most will immediately picture its artificial intelligence, the smooth motion of its arms, or its ability to work for hours on end thanks to the 4,680 battery pack. But for those in the industry, the deeper and less often discussed story lies in the skeleton, the structure responsible for bearing the full load, transmitting force, absorbing impacts, and ensuring every movement is executed with precision. So, how does the process of selecting metal materials for Tesla Optimus take place? Before we begin, if you love staying ahead on Tesla and AI tech, hit subscribe now. You'll be the first to know the breaking news. When the Optimus project first kicked off in 2021, we began with materials familiar to the mechanical engineering industry. Standard 6061-T6 aluminum alloy with a tensile strength of 310 megapascals for the main frame. 304 stainless steel with a tensile strength of 515 megapascals to reinforce high load points, and ABS engineering plastic with an impact strength of 250 joules per meter for the outer panels. At that stage, the primary goal was to quickly build a prototype that could stand, walk, and move its arms. No one thought much about optimizing every gram of weight or achieving durability for 10,000 hours of continuous operation. The first-generation skeleton weighed 185 pounds, sturdy enough for testing, but it had poor impact resistance and could deform 2 to 3 millimeters under unusual torsional forces during outdoor trials. When Optimus began facing harsher tests in 2024, climbing 30-centimeter stairs, lifting 40-pound objects, walking on 35-degree inclined surfaces, and enduring simulated accident impacts of up to 30 G, we quickly realized the original materials wouldn't take the project far. New requirements became clear. The frame had to be light enough to keep energy consumption under 500 watts per hour, strong enough to withstand unexpected impacts up to 60 gigahertz, and, more importantly, maintain precise geometry with deviations of less than 0.05 millimeters. So control algorithms wouldn't drift after 1 million operating cycles. After 87 failed experiments and finite element analysis on 2,500 scenarios, Tesla's materials engineering team narrowed the choice down to 3 materials that met the light, strong, impact-resistant criteria. The first was 7075 aluminum alloy, commonly used in aerospace, with a tensile strength of 570 megapascals. This alloy has a very high strength-to-weight ratio, 83% stiffer than 6061 aluminum. Compared to the 2021 version, switching to 7075 reduced the mainframe's weight by 18%, bringing it down to 154 pounds, while increasing tensile strength by 40%, reaching 434 megapascals. 7075 aluminum also offers excellent fatigue resistance, maintaining its shape after 2 million motion cycles with deformation under 0.1 millimeters. The second material is the 6Al4V titanium alloy, chosen for joints and high-stress concentration parts such as the wrists, ankles, and hips, with a tensile strength of 950 megapascals and exceptional corrosion resistance. Titanium maintains its high strength at temperatures from -20 degrees Celsius to 50 degrees Celsius, which is particularly important for outdoor robot operations. Although the cost and machining difficulty of titanium are 5 times higher than aluminum for critical components, it ensures that heavy impacts of 50 gigahertz will not cause permanent deformation, keeping failure rates below 0.5%. The third material is carbon fiber composite, used for the outer protective panels and certain internal struts, with a tensile strength of 1,500 megapascals. Carbon fiber is extremely lightweight with tensile and torsional strength 3 times greater than stainless steel. When properly molded and bonded, it not only protects the internal frame but also disperses impact forces when Optimus falls or collides with a hard object, reducing the transmitted force by 40%. Tesla uses pre-preg carbon sheets and an autoclave curing process to produce components with a precision of 0.02 millimeters, cutting post-production finishing work by 15%. The selection of these 3 materials was not based on theory alone. We carried out destructive tests, from dropping the frame from a height of 2 meters to 50 G impact collisions, to twisting the frame at 2.5 times the expected real-world load. The results showed that the new structure not only withstood these tests, but also recovered its shape with a deviation of less than 0.03 millimeters. Optimizing weight and strength is an ongoing process. Tesla applies a concurrent design model between the mechanical, materials, and AI control teams. When the software predicts that certain parts bear less load, we hollow them out internally or replace them with lighter materials, cutting another 5 kilograms. When collision sensor data shows that a hip joint experienced an unusual 40G load, the materials team switches to titanium alloy or adds reinforced carbon fiber layers, increasing strength at that location by 25%. Thanks to this approach, the Optimus V 3.5 frame is 27% lighter than the first 2021 version, yet can withstand 1.8 times the force, up to 108 G. An indispensable element in the manufacturing process is metal and composite 3D printing technology. For aluminum and titanium alloys, we use powder-based metal 3D printing combined with lasers to create complex parts with 0.01 mm precision, cutting machining time by 30% compared to traditional methods. This technology allows us to build internal lattice structures, similar to the hollow bones of animals, reducing weight by 15% while increasing rigidity by 20%. For carbon fiber, 3D printing enables the creation of composite molds with integrated channels for wiring or hydraulic tubing inside, reducing the number of assembly pieces by 10%. Tesla makes no secret of its ambition for these materials and techniques to go beyond robotics. Aluminum and titanium alloys have long been standard in aerospace and defense, but they are now manufactured with 0.02 mm production accuracy and at 25% lower cost thanks to Tesla's production lines. Smart reinforced carbon fiber composites could find their way into ultralight EV chassis, impact-resistant battery structures with 30% greater durability, or handheld medical devices that require minimal weight yet maximum strength. Looking back on the journey since 2021, Optimus's frame is far more than a mere material upgrade. It is the result of 12,000 hours of simulation analysis, 150 real-world tests, and a data-driven design mindset. If Optimus can work in a factory environment for 16 hours a day, walk the streets, or lift 165-pound loads without damage, the credit goes largely to the silent skeleton built from materials once thought to belong only in aerospace. Elon Musk once told us during a technical meeting, "If you want a robot with the strength of a human but the energy consumption of a laptop, then every milligram of material has to be worth it." And with Optimus V3.5, we've come very close to that goal, with energy consumption reduced by 35% compared to the 2021 version. Not through magic, but through the sum of material choices made over the past 4 years. Choices that seemed crazy at first, but have proven to be the key to turning an idea into a powerful, durable humanoid partner ready to step into the real world. How Tesla optimized the cost of materials to make Optimus. In developing Tesla Optimus, one of the most critical factors in achieving performance, durability, and scalable production at a reasonable cost was selecting the right material for the metal frame. From the very beginning, the engineering team narrowed down 3 primary contenders: 7075 aluminum alloy, titanium, and a high alloy steel with nickel content. The goal of the testing was not only to evaluate mechanical properties, such as tensile strength, fatigue resistance, impact tolerance, and corrosion resistance, but also to analyze both the testing cost and the material cost per Optimus unit in mass production. This was a problem that combined both engineering and economics. A material that performs well mechanically but is too expensive would eliminate commercial viability, while a cheaper material that is heavy or lacks durability would significantly reduce the robot's operating time and reliability. The testing process lasted 5 months, progressing through multiple stages from digital simulations to real-world trials. Each type of material was used to manufacture a full prototype frame, keeping the design identical but completely changing the primary material to allow direct comparison. For 7075-T73 aluminum, manufacturing a prototype frame cost around $7,500, thanks largely to its suitability for fast CNC machining and metal 3D printing. Mechanical and environmental testing for this material cost approximately $18,000, covering tensile, compression, impact, fatigue, and corrosion tests, bringing the total testing cost per prototype to roughly $25,500. Titanium, on the other hand, due to its higher raw material cost and greater machining difficulty, cost as much as $26,000 just to manufacture a prototype frame, plus about $22,000 for testing, raising the total cost to nearly $48,000. Meanwhile, the high alloy steel had the lowest manufacturing cost at around $6,000, with testing expenses of about $17,000, totaling $23,000 per prototype. In the end, testing costs were only part of the equation. Tesla also had to consider material costs for mass production. The Optimus V3.5 frame weighs about 55 pounds. If 7075 aluminum is used as the primary material, the most efficient material allocation is roughly 85% of the weight in aluminum, 10% in titanium for critical joints, and the remaining 5% in carbon fiber composite to reduce weight and increase stiffness in specific areas. With average prices of $12 per pound for 7075 aluminum, $60 per pound for titanium, and $80 per pound for carbon fiber, the material cost for a complete frame comes to approximately $566. When scaling the calculation to 10,000 Optimus units per year, the cost differences become significant, with the hybrid approach of using 7075 aluminum as the primary material. The total annual material cost comes to about $5,660,000. Factors such as stable sourcing, machining speed, and compatibility with metal 3D printing technology also play decisive roles. 7075 aluminum has a major advantage, with abundant supply from the aerospace industry, easier machining compared to titanium, and faster 3D printing capabilities, reducing frame production time from 6 days to just 3.5, thereby accelerating time to market. Tesla's final decision was to select 7075 aluminum as the main material for most of the load-bearing frame, combined with titanium for critical joints and carbon fiber for lightweight panels and struts. This hybrid approach strikes a balance between technical performance and economic efficiency, making Optimus both lightweight and durable, while keeping material costs reasonable for commercialization. Within the projected selling price of around $20,000 for Optimus, the material cost of the frame accounts for only about 2.8%, allowing Tesla to allocate more of the budget to other critical components such as the drivetrain, sensors, and AI brain. The hundreds of thousands of dollars invested in the early testing phase were therefore far from wasted, as they ensured that when Optimus reaches the market, it will not only be powerful and durable but also priced for large-scale production, fully aligned with Elon Musk's philosophy that every gram of material and every dollar spent must serve the ultimate goal: creating a humanoid robot capable of working efficiently alongside humans at the lowest possible ownership cost. How Tesla Optimus become the best homemaker. Tesla's Optimus version 2.5 can currently handle about 1,500 basic tasks, but version 3 is expected to potentially double that number due to its expanded capabilities. The increased degrees of freedom make it more precise and versatile, so reaching 3,500 tasks is entirely feasible. However, Elon Musk has acknowledged that developing Tesla Bot version 3 is a formidable challenge. Every component, from motors and gearboxes to sensors and power electronics, must be custom-built by Tesla, as no off-the-shelf parts meet the robot's advanced requirements. A recent 44-second video by Figure's CEO Brett Adcock showed the Figure 02 robot picking up laundry items and placing them in a washing machine, repeating the action 9 times in under a minute. Yet, it stopped short of adding detergent or starting the machine, indicating limitations in completing the full laundry process. In contrast, Tesla's Optimus was showcased dancing across a factory floor, performing spins, slides, and rapid movements with flawless balance, unsupported by wires or visual effects, as confirmed by lead engineer Milan Kovac. While Figure 02 excels in delicate hand movements such as handling soft fabrics, Optimus outshines it in full-body mobility, speed, and stability. With Optimus's newly upgraded 22-joint hand, mastering tasks like handling soft items is only a matter of time. Musk emphasized the complexity of the project, noting that every part is designed from first principles, including motors, sensors, and control electronics. Tesla is leveraging neural networks, similar to those used in its self-driving cars, to train Optimus's limbs and sensors. Musk likened Optimus to Tesla's electric vehicles, describing both as robots optimized with the same AI techniques. Musk also shared ambitious plans to scale Optimus production, targeting up to 100,000 units per month by 2030, a goal he believes is achievable but challenging. He admitted that the initial 1 to 2 years will be tough, with potential supply chain issues or technical setbacks, especially as new features are added to version 3. These challenges align with Tesla's history of production scaling difficulties. At the Tesla lab, creativity is a dense atmosphere, permeating every hallway conversation and every round of testing on the freshly printed skeletal frames of Optimus's hands. Though these are not the final versions, they stand as proof of the constant evolution in perfecting what is considered one of Optimus's most critical components. With 24 degrees of freedom to achieve dexterity close to that of a human hand, they allow the execution of complex manipulations with an accuracy of up to 0.1 millimeters. We draw no strict lines between the software and hardware teams. A mechanical engineer can just as easily propose an improvement to a control algorithm, while an AI programmer might suggest changing the knee joint material to reduce friction by 15%. Elon Musk encourages this blend with a simple principle. Every technical limitation is an opportunity for creativity. By the end of 2024, a period of sweeping changes had begun. In just 4 months, Optimus went through 42 software upgrades and 6 hardware overhauls. Part of the reason came from what Elon calls the compressed evolution cycle. We don't wait until a system is fully perfected before testing it. Instead, we continuously feed in small improvements, allowing the robot to learn while operating. New 12-megapixel vision sensors, an image processor optimized to cut latency down to 8 milliseconds, multi-channel object recognition algorithms with 98% accuracy, all of these were integrated without disrupting the overall architecture. In January 2025, I witnessed one of the most spectacular changes, the hand-eye coordination system. Previously, Optimus could only determine the location of an object and move its hand toward it. Now, the robot can adjust its movement behavior based on direct feedback from its fingertips, just like how a human instinctively readjusts their grip when they feel an object starting to slip. This was not just a software update. We had to redesign the tactile sensing structure inside the fingertips, crafting it from synthetic materials with elasticity equivalent to 90% of human skin, and improve the micro-actuators to respond 35% faster, achieving a reaction time of under 10 milliseconds. The electronic skin, developed by researchers from the University of Cambridge and University College London, can be melted down and reshaped into complex forms. This technology senses and processes a wide range of physical inputs, enabling the robot to interact with the physical world in far more meaningful ways. Although the robot's skin is not as sensitive as human skin, it can detect signals from over 860,000 sensor channels embedded in the material, allowing it to recognize different types of touch and pressure, such as finger taps, hot or cold surfaces, damage from cuts or punctures, or multiple simultaneous contact points within a single material. Combined with the 22 degrees of freedom in hands that are the most advanced in the current robotics market, Optimus is already demonstrating an unlimited range of capabilities, with the ability to handle over 1,000 different tasks in real-world environments. In the laboratory, everything feels amplified. Here, Optimus is tested through standard exercises, sorting objects at a speed of 50 items per minute, assembling battery modules with 99.5% accuracy, walking on uneven surfaces with inclines of up to 30 degrees, and communicating through language and gestures with a fluency level reaching 95% of that of a human. Our workbenches are covered with high-speed cameras recording at 120 frames per second, force gauges with a sensitivity of 0.01 newtons, torque analyzers, and entire server arrays for simulations with a computing power of 10 teraflops. Software engineers often stand beside robot skeletons with their frames fully opened, simultaneously checking control circuits and modifying code in real time. There are no barriers between lines of code and mechanical components. But when Optimus steps into the real world, the story changes. In the factory, the robot must contend with continuous noise levels reaching 100 decibels, lighting conditions shifting from 100 to 1,000 lux, and objects moving unpredictably at speeds of up to 2 meters per second. Humans may pass by, sometimes even interact unexpectedly. We realize that AI must not only be accurate but also humble, meaning it should be ready to yield, wait, or adjust its behavior to fit the social context, achieving a collision avoidance rate of 99.5%. In the lab, everything is controlled. Out there, the world is a chaotic system that Optimus must blend into. Elon often appears in both settings, sometimes stepping into the lab in the middle of a test, other times going straight to the production line to see Optimus working alongside humans. He has a habit of asking questions that seem impossible to answer on the spot. If Optimus can learn to assemble faster than an engineer after 1 week, why can't we teach it to do that in 1 day? That question forces us to rethink the entire AI training pipeline, from simulation to real-world data, from reinforcement learning to context-aware adjustments, reducing training time for certain tasks from 7 days to just 24 hours. I remember one February afternoon in 2025 when Elon Musk requested that we build a mock neighborhood inside the testing warehouse. Streetlights, signboards, small shops, even other robots pretending to be pedestrians. The reason was simple. If Optimus is only good in a factory, it will remain just a machine. If it can thrive on the streets, then it will truly be a part of humanity. That very evening, the mechanical team began assembling the modules, while the AI team installed traffic scenario processors and crowd behavior algorithms. Within just a week, Optimus was able to cross marked pedestrian lines, avoid bicycles traveling at 6 miles per hour, and recognize traffic light signals with 98% accuracy. Every time Elon spoke with us, I noticed one thing. He didn't care about comparing Optimus with competitors in the usual sense of winning or losing. He would only ask, "Is it good enough that your child would trust it?" That question changed the way we measured success, not by the number of tasks completed, but by the quality of the human experience when standing next to Optimus, with safe interaction rates reaching 99.9%. In March 2025, we conducted a special trial, having Optimus work alongside a team of technicians on the 4,680 battery production line. In the lab, operations are pre-programmed and tightly controlled. But in the factory, Optimus had to improvise when equipment malfunctioned, when colleagues gave hand signals instead of digital commands, when a pallet of batteries was placed slightly off its designated spot. The result was that the robot not only completed its tasks, but also suggested improvements to repositioning that optimized the workflow, something we had never expected to happen at this stage, boosting production line efficiency by 15% and reducing errors to below 1%. When Elon heard the report, he simply smiled. When it starts teaching humans, we're on the right track. That was when I realized his vision didn't stop at creating a capable robot. It was about creating a true collaborator, an entity that could observe, learn, adapt, and improve the systems around it, with the ability to handle over 100 different tasks. Workdays at the Tesla Optimus lab always begin with an open-ended question and end with a new prototype. Between those two moments lie hours of code revisions, 3D printing components, testing sensors, logging data, and heated debates. Creativity here doesn't come from having free time. It comes from constant pressure and an almost unshakable belief that everything can be done faster, better, with the goal of producing 5,000 Optimus units by the end of 2025. Looking back from early 2024 to early 2025, I can see clearly why Optimus keeps changing. It's not a reaction to errors or competition. It's the very nature of how Tesla operates. Try, fail, learn, and then improve. All of it happens at a pace that never allows you to stand still, with more than 50 hardware and software versions updated along the way. Elon never gives us time to be satisfied with the current build. Every time we reach a milestone, he asks, "Good, now what?" I leave the lab tonight as Optimus is being trained on dozens of new skills. They may sound small compared to walking the streets or assembling batteries, but to Elon, every action, no matter how minor, is an opportunity to optimize, to learn, and to make the robot more human-friendly, with a folding speed of 90 pieces of clothing per hour and 95% accuracy. And as the lab doors close behind me, I know that tomorrow will start with a new question, and Optimus will change again. Not because it isn't good enough, but because at Tesla, better is always mandatory. How does Tesla Optimus plan to move on any terrain? Let's start with the perception system, often referred to as the robot's eyes. Tesla has adopted a vision-only approach, eliminating the reliance on complex sensors like LiDAR or radar, similar to the full self-driving system used in Tesla's EV. Optimus is equipped with a high-resolution camera array, up to 12 cameras in Gen 3, that provides continuous image data streams at 4K resolution and 60 frames per second per camera. This effectively delivers nearly 1,000 frames per second in total, enabling the robot to process over 1 billion pixels every second. The onboard artificial neural networks trained on an enormous dataset of up to 10 petabytes from indoor environments, enable the robot to analyze images in real time. Result: Optimus develops an occupancy grid, creating a digital 3D map with up to 99.9% accuracy. This map clearly distinguishes between free space and areas occupied by obstacles or nearby objects, such as humans. For example, in a small household with 3 to 5 people, including children and the elderly, the grid can scan and update the environment in just 50 milliseconds. This allows the robot to avoid collisions with a remarkable 99.9% success rate in simulation tests, drastically reducing the chance of impact-related falls for humans to just 0.1%. This quite evidently positions Tesla Optimus as the ultimate homemaker we've been envisioning. To enrich the occupancy grid, Tesla integrates visual markers, unique features tied to specific locations captured by the cameras, such as the edges of machinery or battery trays, found in a factory setting. These markers play a crucial role in determining and tracking the robot's position with sub-centimeter accuracy, even in low-light environments, thanks to an infrared camera. According to Elon Musk, the system has been upgraded to include over 1,000 markers per square meter, enabling Optimus Gen 3 to achieve twice the localization precision compared to Gen 2. However, vision is not enough. The robot must also maintain balance and move smoothly, especially considering that Optimus Gen 3 features around 40 motorized actuators, amounting to over 200 degrees of freedom when including secondary joints. This is where the simulation system comes into play. The Tesla team has integrated the robot's motion code with the autopilot simulator, a tool previously used to train self-driving cars across billions of virtual miles. Within this simulation, Optimus can test and optimize its walking style, select gait patterns, and adjust other parameters to safely navigate indoor environments. The simulation enables precise actuator activation with torque ranging from 10 to 100 Newton meters, ensuring that the robot maintains balance even on uneven terrain with up to a 20-degree incline. Test results show that Optimus achieves a 98% success rate in balance retention after 1 million simulated cycles, reducing energy consumption to just 2.3 kilowatt-hours for 10 hours of continuous operation. One of the greatest challenges is replicating the human ability to walk. For humans, walking is second nature, but for robots, it is a complex problem involving hundreds of variables: terrain, robot weight, payload, environment, and many others. Tesla began by developing a comprehensive digital model that includes kinematic properties, dynamics, and contact behavior. This model, combined with environmental conditions and the target destination, is fed into the planning system to generate a reference trajectory, a sequence of paths from origin to destination, extending up to 100 meters within a factory setting. The trajectory generation process consists of 3 main steps, making the system exceptionally efficient. First, the system plans a complete path from start to finish, represented by a curved white line in the demonstration video, with an average length of 50 meters and a planning time of just 100 milliseconds. Second, the path is divided into smaller segments, each approximately 5 to 10 meters in length for easier management. Third, the gait is finalized for each segment, including walking speed, up to 1.5 meters per second in Gen 3, as well as the type of footsteps and actuator intensity. The result is a comprehensive trajectory that combines the planned path with detailed footstep parameters, achieving a 45% energy savings compared to Gen 2, while maintaining balance even when carrying a 45-pound payload. In the demo video showcasing movement over uneven terrain, you can see the real-time center of mass tracking system refining the trajectory to prevent falls, with an impressive 99.5% success rate. However, the real world is not an ideal simulation. It is dynamic and full of surprises. This is where motion control and state estimation systems become crucial. In an ideal world, the planned trajectory assumes a static environment, but in reality, conditions are highly variable. Humans move around, sometimes up to 50 people on a factory floor. Forklifts operate at speeds of 2 miles per hour, and subtle changes such as slippery floors due to grease may occur. These factors can destabilize the robot, leading to potential falls. What would you want Optimus to do for you if you could control it with your thoughts? Maybe it's cooking your famous recipe or reading to your grandkids. Share your ideas in the comments below and let's think about the future together. If you enjoyed this video, please give it a thumbs up and subscribe for more stories about the technologies shaping our world.